Good morning, everyone. My name is Changjong. I'm currently working at the Rutgers University. So today I talk about the strong interband interaction in the excitonic insulator phase of tantalum to nickel selenide. So this work was done before I joined the Rutgers University. So before starting, I would appreciate my collaborator in this study. So Manjin and Jun-Sung Kim made a single crystal sample, and Jun-On Lee and Han-Ung Yeom did the scattering tunneling microscope and scattering tunneling spectroscopy measurement. And I and B.I. Min provided the theoretical interpretation in the experimental result. Then what is an excitonic insulator? So this terminology was first introduced by the Walter Kang in the 1967. So let me briefly introduce his basic idea in the excitonic insulator. So imagine that we have a semiconductor with one valence band and one conduction band. So it shows a clear band gap denoted by a letter G. And here is the exciton band. It is inside the gap region. So exciton binding energy could be estimated from the energy difference from the exciton band and the bottom of the conduction band. So when the band gap is smaller than the exciton binding energy, then the exciton forms simultaneously. In other words, the excitonic instability happens, and it divides the system into the excitonic insulator. So when the valence and conduction band are separated by a finite momentum W in a momentum space, then the excitonic instability triggers the charge density wave transition. So due to the charge density wave transition, some spectral weight of the conduction band is transferred to the valence band maximum point, and the band dispersion looks like this. And due to the excitonic interaction, the band is renormalized, and this is actually the electron structure of the excitonic insulator. So when you apply the external pressure into the excitonic insulator, then you can meet another excitonic instability, and the band is, renormalized further. So in principle, the successive excitonic transition could happen under pressure. So in the insulating side, the excitonic condensation can be described by the Bose-Einstein condensation. So this excitonic insulator could be realized in the semi-metallic system. So in the semi-metallic side, the band gap is simply replaced with the negative band gap. So again, when the band gap is smaller than the exciton binding energy, then excitonic instability happens. So in this case, the number of charge carrier becomes smaller, and the charge density fluctuation happens. So it triggers the exciton transition. But however, the excitonic condensation is somewhat different from the insulating side. So in the insulating side, the exciton condensation follows the Bose-Einstein condensation, but in the semi-metallic side, the excitonic condensation follows the BCS type condensation. So let us turn into the main material, tantalum to nickel selenide. So it has the layered structure, and the boundary-wise interaction act along the B-axis. So in the view along the B-axis, the quasi 1D chain structure is clearly realized. So here the chain direction is along the A-axis. So here the nickel chain is sandwiched by the tantalum double chain, and the crystal structure surrounded by this line is basically the basic component of the crystal structure. So this basic element is repeated along the C-axis. So it is noteworthy that the tantalum atom is surrounded by selenium atom octahedrally, but the nickel atom is surrounded by the selenium atom tetrahedrally. So therefore, the tantalum, So the tantalum D level is split into the low line T2G and high line EG level, but the nickel D level is split into the opposite order. So let me describe the electron structure. So since the basic crystal element possesses the one nickel chain and two tantalum chain, the electron structure could be described with the one nickel side and two tantalum side. So in the ionic picture, the tantalum and nickel have the 4+ and 2+ valence state, which correspond to the D1 and D8 system respectively. So the 1 electron occupies the T2G level in the tantalum side, and the 8 electron occupies the nickel side. So here the EG level is fully occupied and the T2G level is partially occupied. So the tantalum and nickel side provide the electron and hole respectively. So tantalum provides the conduction band and nickel provides the valence band. So this electron configuration can be replaced with the two holes in the T2G level. So therefore, this electron configuration suggests that this system is a semi-metal. Then how can we realize the external insulating band in this system? So answer is pretty simple. If one electron in tantalum side and one hole in the nickel side form an extern, then external insulating band could be realized in this system. So at this point, I'd like to emphasize that the external insulating band in this system is driven from the semi-metallic side, not from the insulating side. However, it's still controversial whether the external insulating band is driven from the insulating side or from the semi-metallic side. So let us look at the previous study in this sample. So in 1986, these also measure the electrical resistivity depending on the temperature. In the data of the derivative of resistivity with respect to temperature, it shows the anomaly at around 320 Kelvin. Actually, this temperature coincides with the structural phase transition temperature. And the 2009 Japanese group did the RPS measurement in this sample, and they found that an unusual flat band near the gamma point. So due to this unusual behavior, this sample is proposed to be an extonic insulator. Also, the temperature-dependent RPS measurement was done in 2014. At low temperature, 40 Kelvin, the flat band is also detected near the gamma point, but this flat band is still low, but even at high temperature. So high temperature, it showed a clear gap picture. So therefore, this also argues that the high temperature phase is a semiconductor with a finite band gap. So therefore, the external transition is in the BEC region. However, their argument was questioned by another experiment. So recently, Lu et al. Did the optical measurement in this sample, and they found that the optical gap is about 0.16 eV at 150 Kelvin. So this optical gap is reduced further upon heating and eventually disappears at high temperature. So therefore, they argue that the high temperature phase is a zero-gap semiconductor, and the external transition is close to the border of the BCS and the BEC region. So therefore, high T phase is still controversial, so it is necessary to clarify this issue. So several important issues remain in this sample. So first, there is no scavenger microscope and spectroscopy study. So for the first time, we studied the real space electron structure by using the STM and STS measurement. And second, the energy gap of the external insulating band has not been fully determined yet. So we used the STM and STS, and we measured the energy gap is about 300 MeV. And the next, the experimental evidence of the external insulating band is mostly indirect. So in this study, we provide another evidence of the external insulating band, and we also observed the strong interband interaction in this sample. And finally, the external transition is still controversial. So in this study, we argue that the external transition is close to the BCS region, and the Nomad Base is a semi-metal. So let me start. So we used the surface sensitive, the STM and STS to study the electron structure. So in order to get the STM topography, we set the bias voltage at 250 millivolt and the tunneling current at 300 picoampere. So this setting allows the constant height between the STM tip and the surface of the sample. So we scan the sample along the Z-axis as shown in this figure. So along the Z-axis cross the nickel and the tantalum chain. So since actually the gray atom is a selenium atom, so since the selenium atom are in the outermost surface layer, so STM tip just follow the height of the selenium atom. So this is the STM topography. So it shows the clear 1D chain behavior. So here the chain direction is along the A-axis, and the C-axis is across this chain. And this is the 3D version of the STM topography. So it looks like the sinusoidal behavior. So it indicates that the measurement captures the corrugation of the surface selenium layer. So here the top to bottom distance is 0.16 nanometer, which corresponds to the distance between the highest line and lowest line selenium atom. So when you zoom in a certain area in the STM topography, the clear atomic arrangement is realized. So here, the selenium atoms are aligned along the red dotted line, which is along the A-axis. And so here, the bright color and dark color represent the high line and low line selenium atom respectively. So here we observe the monoclinic angle, which is consistent with the previous crystallographic measurement. So when you compare with the crystal structure, the red dotted line is consistent with the atomic arrangement of the selenium atom in the crystal structure. And also the selenium atom follow the sinusoidal behavior. We observe the sinusoidal behavior were matched up with the atomic arrangement of the selenium atom in the crystal structure. So we also measure the temperature-dependent, the DIDB, which is consistent with the density of state. At high temperature, 300 Kelvin, it shows the finite value at zero bias voltage. So here, the zero bias voltage corresponds to the Fermi level. So therefore, it shows the metallic behavior. At the low temperature, 78 Kelvin, it shows a clear band gap picture. So therefore, the metal insulator transition happens in this system. So here, the size of the null density is the 0.16, which is consistent with the optical gap in the previous experiment. However,
excuse me, may I ask a technical question? On the left picture, is the 0 point of the DIDB really at the bottom of the graph?
This one?
No, the left-hand one, the 300K.
This one.
Yeah, where is 0? Is that at the bottom of the graph?
Not quite.
You mean this one?
Yeah.
So this is as the finite value.
Right. What I wanted to know was where 0 was. If you put y-axis, I understand that it's normalized, but there's a point which is 0.
Oh, actually, this is the zero value.
Okay, that's what
right.
And when I go to here, the 0 value in your experiment is the dashed lines.
Mm-hmm.
Okay, that's what I wanted to know. Thanks.
Right. However, considering the sum of broadening, so it is more natural to assign the gap size the peak-to-peak distance. So here, the peak-to-peak distance is the 300 MeV, which is the genuine energy gap in the excitonic insulator. We also measured the tunneling current versus the bias voltage at two different temperatures, 78 and 300 Kelvin. So here, as you can see, the 300 Kelvin shows the metallic behavior, but the 78 Kelvin shows a clear gap picture. Here, the size of this line is 300 MeV, which is exactly same as this peak-to-peak distance. So therefore, the metal insulator-based transition is also supported by the tunneling current, and the energy gap is the 300 MeV. And this figure shows the normalized DIDB plot of the STS measurement at 78 Kelvin. So this is the real space electronic structure. Here, the x-axis means the atomic position in the crystal structure along the z-axis, and the y-axis presents the energy level. So again, the zero bias voltage means the Fermi level. So the energy below zero means the occupied state, and energy above zero means the unoccupied state. So here, the peak of the occupied state corresponds to the tantalum position in the crystal structure, and the peak of the unoccupied state corresponds to the nickel position in the crystal structure. So this behavior is well demonstrated when we draw the DIDV profile at a selected energy level indicated by red and blue arrow. So here again, the peak of the conduction band corresponds to the nickel position, and peak of the valence band corresponds to the tantalum position in the crystal structure. So it means that the valence band maximum is localized on the tantalum side, and the conduction band minimum is localized on the nickel side. But reminding that the tantalum and nickels are D1 and D8 system respectively. So tantalum provides the conduction band, and the nickel provides the valence band. However, the STS measurements show the opposite trend. So therefore, the STS measurements show the band character inversion. So in order to interpret the experimental result more thoroughly, we adapted the two-band Falkov-Kimball model. So the model Hamiltonian has the two components, H0 and H prime. So here the H0 is a non-interacting Hamiltonian and consists of the band energy of valence and conduction band. So here the epsilon V and epsilon C are the non-interacting band dispersion energy of the valence and conduction band respectively, and the D dagger and C dagger are the creation operator of the valence electron and the conduction electron respectively. And here the H prime is the interaction Hamiltonian, and it shows the Coulomb interaction between the valence and conduction electron. So here the VC is the screen Coulomb potential. So the tantalum to nickel selenide show the structural phase transition from orthorhombic to monoclinic upon cooling, and this structural phase transition is associated with the gamma point phonon mode only. So it excludes the CDW transition. So therefore, we focus on the external model near the gamma point. So we solve this model Hamiltonian within the mean field level. So we introduce the external order parameter like this. It is similar to the order parameter in the BCS theory. Then we can write down the Green function for the valence and conduction band in terms of the external order parameter. So since the pole of the Green function describes the band dispersion, then we can obtain the renormalized valence and conduction band. So here I'd like to emphasize that the renormalized valence and conduction band depends on the external order parameter. So now it is time to apply the external model into the real problem. At first, we obtain the DFT band dispersion in this system. So here, as you can see, the nickel band has a valence band has the nickel D character, and the conduction band has tantalum D character. So for simplicity, the outermost valence and conduction band are chosen and approximate to the parabolic band dispersion. So we assume that the DFT describes the non-interacting Hamiltonian, so therefore this band dispersion represents the non-interacting band dispersion. So therefore we can obtain the non-interacting band dispersion from the DFT calculation. So simplified, the Nomad Base band dispersion is obtained from the DFT calculation. So when we introduce the external interaction in the Nomad Base and set the order parameter as the 150 MeV, then the resulting band dispersion looks like this. It shows the clear band gap. So when you compare to the STS measurement, the gap size is well match each other. Also, when you compare to the RPS measurement, the observed flat band is also well captured in the external model calculation. Also, this external model also shows the band character inversion. Here, the top of the valence band has the tantalum D character, and the bottom of the conduction band has the nickel D character. So this band character inversion is also well demonstrated in the calculated spectral rate. So here, near the gamma point, the valence band has more tantalum D character than nickel D character, and the conduction band has more nickel D character than the tantalum D character. So therefore, this extra model will present the band character inversion near the gamma point. So far we consider that the Nomad base as the semi-metallic base. But what happens if we consider the semi-conducting Nomad base? So this is the case for the semi-conducting Nomad base. So here the Nomad base shows a small gap picture near the gamma point. So when you introduce the external interaction to the Nomad base and set the external order parameter as 150 eV, then the renormalized band disposition also shows the flat band near the gamma point. However, in this point, the band character inversion does not happen in this case. So therefore, the band character inversion is only realized in the semi-metallic side. So therefore, the Nomad base of the tantalum to nickel selenide is just semi-metal. So this is our summary. So first, we investigate the real space electron structure for the first time, and we measure we observe the metal insulator transition in this system. Also, we measure the energy gap at the 300 MeV, and we also provide another evidence of the extonic insulating phase in this system, and we argue that the Nomad base is semi-metal. Thank you for your attention.
Thank you. Any comment, question? Dennis?
So I have, this question of the band is going to be about the band inversion.
Mm-hmm.
My understanding of it is that there are two origins of a band inversion. One is that I have some hybridization between the bands, which leads to the band inversion, or I have interaction effect, which you have described. So do we have any, from your data, how are you able to distinguish these two scenarios? So single particle hybridization versus interaction effect, which would be excitonic insulators.
Okay, so even if we consider the band hybridization in the Nomad base, it cannot explain the huge energy gap observed in the STS data. So therefore, in order to explain the energy gap observed in the STS measurement, we need to introduce the interband interaction in the Nomad base.
So you're saying a single particle hybridization is just too small for something like this to happen? Okay, and this is probably consistent with you?
So these hybridization numbers were not too large.
Okay.
Yeah.
Okay.
Andy?
So two questions. First, just about data. So your low temperature gap was 300 millivolts, give or take distance between. I thought the optical gap was less.
Yeah, right, 0.16.
So do you know why the difference? Is it an interesting difference, or is it?
Yeah, actually the optical gap corresponds to the activation energy, right? But usually the activation energy is smaller than the real band gap size. So I think that, actually the optical measurement data detect the activation energy, and this data observe the real gap size.
I don't think this explanation works, no? I mean, the optical gap
It's 2 times.
is a direct gap, so,
Yeah.
you know, in all generality, it's going to be smaller than the spectroscopy.
Okay, so I also, show the data. So here, in the STS measurement, the size of the null density is the 0.16, which corresponds to the optical gap. But when you're considering the thermal burdening, where actually the genuine energy gap is the peak-to-peak distance. Also, this gap picture is also captured by the tunneling current measurement.
So what you're saying really is that if we could magically take the broadening out of the optical measurement, then we would see 300. That's the real statement.
Yeah.
Okay. Now, the other thing, which is just wild speculation, we heard from Malta's beautiful talk and others that in the excitonic insulator phase there is a symmetry breaking, inversion symmetry breaking, which leads to a little bit of structure in the density of states, the minimum point of minimum band gap is not exactly at the gamma point. There's a little bit of asymmetry. So my question, would that show up in a QPI measurement, which sort of shows Fermi surface? Is there a way to see that in your experiments? I mean, it's a delicate effect, it's long wavelength, but could you see that off-centering somehow, for example, by QPI?
Well, actually, yeah, I didn't consider this effect. But actually, in this study, we would like to interpret this situation easily with the minimum, model, So therefore, so we applied a simple model Hamiltonian, and only consider in the interband interaction in this system. Probably the next step, probably we need to consider the other impact and to see what happened in the system.
However, I think we should just go back to the question of the optics. I don't know if you were going to. I still don't understand it. That the fact that the gap in the STS is twice the gap in optics. And I think there has to be something different to the explanation you made, because this cannot be the explanation. It's not broadening. Cannot be broadening.
I don't believe it.
So I'm not explaining that, but I'm sure it's not broadening.
Just one comment on it. So could it be that your measurements are very sensitive to gamma point only? But in optical data, we can really see closer.
The point of minimal gap, which is not at gamma point.
Not at gamma point. Maybe it's really interesting.
This might be incorrect, but I think this.
Maybe it's really, I don't know.
But here the.
Would you show us the data between 300 Kelvin and 78 Kelvin? Do you have data? That sudden change. Is that the? Would you show us the data between 300 Kelvin and 78 Kelvin? You don't have that data? Yeah, these two. Between
no, we only have the 378 Kelvin data.
That's right. Sorry?
So we only have the two temperature data.
And standard understanding that the 300 Kelvin, the resistivity measurement indicates that the system is insulated. Okay? But that is, then you have the final thing.
Well, I mean, the optical measurement show where it's a nearly zero gap picture. But
you have a very big zero energy.
No, what he's
still states. But that indicates that it is a.
You go to your data.
Okay.
Not to your data, to the STS data.
Okay.
I think what you're mentioning is that there is a finite value of which is high for the zero bias, which is inconsistent with the.
Yeah, that's very big.
That's what you are saying, no?
Sorry?
Yeah.
That's what you are saying.
And so therefore, I want to see the data between 300 Kelvin and 78 Kelvin, if you have.
Okay, but unfortunately, currently we have only two temperature data.
A very, very naive question, but if you just take this data and you extrapolate the gap by just, I guess you said the same thing. If you just now take the slope, extrapolate the gap to the place where the conductance goes to zero, you will find also something like 170 millivolts. It's the same as the one in the optical.
Probably.
So it's the same.
There's no controversy. It's some kind of semantic. It's definition.
But in this study, I'd like to argue that the STS measurement observed the band character inversion, and this band character inversion is only explained when we consider Nomad Base as the semi-metallic base. So this is another evidence of the semi-metallic high temperature base.
That one I don't see. There was another comment. If not, we thank the speakers and